Thank you very much. Also welcome from my side, and I'm glad to be here to present the program Digital Power Plant. Unfortunately, it's not about, we have interruption. It's not about digitally producing energy, what would be very valuable at the moment, but it's about digitalization of our value chain. And my agenda looks quite similar like that one of Johannes. And firstly, I want to make sure that you see who SBB is, SBB Energie, to motivate the following examples I will show to you. And firstly, I have a geographical overview of our power infrastructure, telling you that SBB Energie is a fully vertically integrated energy supplier to railway electricity, and not only to SBB itself, but also to the third-party railway companies, providing them energy as a system leader, and means system leader for electricity is 16.7 hertz. And we design our grid and assets, we build and carry on constructions, we maintain, we asset manage them, and we trade and distribute energy. And you have the quality structure on the upper right, and telling you that SBB Energie owns about 5% of the hydropower in Switzerland. And in comparison, we have about 4% of Swiss energy demand in a yearly manner. And going to the next slide, showing you the business case we can do for energy suppliers of our customers. The hydropower plants are mostly in the 60.7 hertz grid, and we're covering about 75% of the demand within our own grid. And the excess demand we have to import from the 50 hertz grid over the frequency converter. You see let's just see at this stage here, and bearing in mind that we are end consumer at the Swiss grid level. So for each kilowatt hour imported, we have to pay grid-in tariffs and cost-covering tariff as well, and that lets us not optimize our power plants as well as the one in the 50 hertz market. The upper left or the upper right numbers only I want to mention is the turnover in gigawatt hours, and telling you that we are about the same size as the city of Zurich consumes in Switzerland. So the railway in Switzerland consumes as much as a city of Zurich. And that leads me to the next comparison with the city of Zurich. It's the demand power over a day. And on the right side, you see the demand power pattern of SBB. And on the left side, that one of the city of Zurich, telling you that we have much more challenging in demand, also in power demand, and we have gradients up to 300 megawatt a minute that we have to cover, and telling you as well that demand side management is very precious to our grid. So coming now to the program, Digital Power Plant, and that started at the end of 2019. And we assessed the field where we expect most value in, and these 4 fields we analyzed are on the left side. We call them virtual operation, we call building information modeling, digital asset management, and work and field force support. And just to have a short introduction to this field, virtual operation is about the trend in energy business to go to smaller but numerous assets, decentralized assets. You can think of operating flexibility with batteries. You can think of solar cells, and that you can't do anymore in future manually. You have to adopt the skill to operate aggregation of assets, and that we call virtual operation. Building information is a methodology, and we understand to design and carry out construction by digital means. As Johannes Manser showed an example with this exploration of transmission paths. And actually, we are convinced that if you want to go digital, you have to take up BIM as it is the birth of the digital representation of an asset if you get on a new asset into your grid. Then digital asset management addresses the trend that asset management goes more to data-driven asset management, condition-based monitoring, higher maintenance strategies like usage-based or condition-based maintenance. We want to get on predictive maintenance, prescriptive maintenance in future, but we are not there now, which are focused in here. And work and field force, we already seen some examples that could be very interesting with anybotics showing robots, but you can also think of what Johannes showed. We're also exploring drone-supported inspection of transmission lines, and you can also enhance the work and field force with IoT, also mostly there are surveillance tasks to fulfill, and here we have many cases going on, and this would have been showed on this slide. I won't explain because of time. Just let you read afterwards when you get the presentation what we do here. But showing you our innovation funnel we have, and also not to read about, all the bubbles are explorations, and certainly we are doing the innovation process like I learned at school. But here I want to mention two cases we have with the EPFL in collaboration with the group of Olga Fink and Menji and Raphael are also here. These red bubbles taking on new AI approaches for analyzing our control system data and learning about early fault detection, what Raphael does, and learning about data-driven efficiency monitoring, what Menji does. And we are I'm quite convinced that that's really promising also in future to support our asset management to have early decisions about their assets and doing more intelligent maintenance measures. But now I want to speak about two other cases which are at the edge of implementation to really nice cases. One is an exploration case about batteries coming into our grid. I will just go on with this, and the other case is a unique one, is a grid restoration within 5 minutes that I want to shortly explain to you, so you will see what we do there. The project BINE is a shorten for a battery swarm in the railway grid. It has its origin from a decision of our board that we want to become 100% renewable till 2040, and this means these 700 diesel-driven locomotives, they have to be retooled in the future, and these locomotives are shunting or construction sites locomotives which have the need to have driving extend without catenary lines in place. And these locomotives will most likely be battery driven in future, and we asked ourselves, what does this mean in terms of opportunities or risk? What do the stakeholders of these locomotives or the fleet manager mean? What their expectations are? Are they willing to cooperate? And what would be the value cases for them and for us? We see us as secondary value cases, surely, because we have to onboard the owners of these vehicles. And so let me just quickly show you the stream we did with the stakeholders, telling you who the stakeholders are on this slide, vehicle owners and vehicle dispatchers and the locomotive drivers have all different needs when dealing with electric or battery-driven vehicles. But in the end, we concluded that the central management of all these electrically driven vehicles with batteries would be of great use. Also, we ran in open doors, I could say, that these stakeholders or these owners of these vehicles have even higher need than we would have in terms of getting a steep learning curve about this new asset coming in, and on the other hand, also battery is a very valuable asset, and we see with battery-friendly charging, they can really get big savings in future. As for the technical aspects, we also did comprehensive simulations with the Berner Fachhochschule, who has a battery model in place, and we applied real data of nowadays shunting and construction site vehicles to simulate what does it mean and to translate what does it mean to a battery-driven fleet. And you see the results on the right side. Our fear to have very high additional load in our grid that's already have spikes of loads in it has disappeared with this simulation. The load extent is about a few percent of our maximum load extent we already have. And another very nice result is that the flexibility of these 250 electric or battery-driven locomotives will show a huge extent of flexibility available at the overhead line. So it's about 60 megawatt hours, and in total they have a capacity of 100 megawatt hours, and 60% is always available for secondary use case, I say in this word. And this is very valuable, and we examined all these value cases, and I only want to mention selection in this time I have. It's the battery-friendly charging, which is promising to give more than 1 million Swiss franc of savings in future to the fleet managers, but this can only be achieved when having a central management platform in place. And in the green box, I want to mention the possibilities of covering extreme load spikes that we do already with heatings, but battery will extend the range of time. Also in summertime, we can use batteries to cover load spikes, and has a great MPV, and also reducing auxiliary services at hydro plants we operate will let us optimize hydro plants better, and has also a great value above 1 million Swiss franc a year. And not to forget about price-dependent loading. This loading is certainly a value that depends on market prices of now, but nowadays it would be very precious. So to conclude, in short, it's a reserve power plant on a silver tablet that is coming to our grid, and really we have to take this opportunity. And if you go to electrical battery-driven vehicles, you go from a pair of pliers to a multifunctional tool. That's one also is aware in the home sector with own EV cars, I think, but that's also the same at the railway, and we're taking up now a collaboration program which goes into implementation and with stakeholders together. Let me come to the other project. I think that's a project unique almost in the world, I would say, that power grid restoration we want to speed up. SBB has once faced a blackout in 2005. Some of you remember probably still. The experience costs are high, and clients are annoyed, and I think the motivation is clear. And since then we train every second year the restoration with our dispatching team. It takes 6 hours about to build up a grid. And our head of grid operation had this very nice idea, not knowing then if everything works and if we really get on, we could that reduce to 5 minutes. And I will speak more than 5 minutes about this project. And within this time, we would have built up the whole grid, railway grid in Switzerland. And let me just tell you what the process is, and the process is on this line here. When you have to restart the grid, then you have to make sure the health of the equipment is there, also there to restart again, and you have to get it into a defined state of the grid, that you have these cells to rebuild and resupply. And firstly, you go to resupply the high voltage level, ramping it softly up and reconnect distribution cells step by step to let the trains operate again. And then you get to a normalized state. And so there are 3 measures for reducing this restoration time. The first measure is the process simplification. That means we re-evaluate the restoration concept and test it by simulation to reduce the number of cells to rebuild, and to reduce, as a consequence, the number of switches you have to do. And you see it in the line down here. Over the next years, we do it in manner fast prototyping to have on the invest always a result in steps. That the number of switches really are reducing very drastically over time. And second mean measure will be automation of the control system. This is actually the measure that brings really fast or speed up, but this has to be done at the end, and relieving the dispatcher to have controlling work at dispatching system, relieving the dispatcher to have the switching work done or acknowledge any notification. And another measure is to do smart logic at the power control, power generator control. So not to have them when having a grid fault to get in enough state, but to analyze what fault appeared and to have it in a very short time to restart and ready to restart again. And we tested this at the field test in last year, and just showing you that we had 2 pilot stations with this new control logic installed at Vernia for a hydropower station and at Fortay for a frequency converter, and tested that at a wide extent from Geneva to Zurich. And, to prove the simulation, to test the adoption of the generator controls, and to also examine transient effects that could appear by measurements. And we tried out different ramp-up times from 40 seconds down to 2 seconds. You want to quickly ramp up, but there are transient effects if you ramp up too quickly. So this has been tried out in this field test, and the results were very pleasing. In fact, the logic did its job, and the transient effects are almost negligible, so that we could speed up the restoring procedure more than expected. And we go on now, have this year a field test also with consumers involved, and the rollout of these generator control features will be also rolled out, will be finally succeeded in 2023, bringing us down in the restoration time by 2 hours, a factor of 3, and the final result we'll get when the control system is updated, and hopefully gets to a minute amount. If it is 5 minutes, we don't know yet, but actually it will be much quicker than before. Thank you very much for your attention. So that's our examples.
Thank you very much.